I love starting off a video by making loud noises on a mic. We left off yesterday after learning how to do bond line structure, labeling these polar bonds, and then discussing about how polar bonds is an indicator about molecular polarity. Can you guys, anybody need one of these? I think a lot of you guys, right? Oh, you printed one off online? Thank you. Who else? From yesterday, yes. Evelyn, you got one? Great. You guys are on top of it. Can you restate that rectangles square analogy that I gave between polar compounds and polar bonds? Do you guys remember what I'm talking about? All squares are rectangles, but not all rectangles are squares. But for polar bonds and polar molecules, I taught him about math instead. Rowan?
Every polar compound has polar bonds, but not every polar bond is a polar bond.
Good. Every polar compound has polar bonds, but not all compounds with polar bonds are polar molecules, polar compounds. Yeah. Did I say that wrong? Did I put too many polars in there? I might have. You guys get it's easier to visualize than say, right? So I gave this example of methane being nonpolar with nonpolar bonds, nonpolar molecule, nonpolar bonds. And why are those bonds nonpolar? Because a bunch of people said so, not because they lack a dipole. Oh. So they're nonpolar bonds because they fall in that threshold that we call nonpolar. Then we said CCl4 is a nonpolar molecule with polar bonds. And then we said something like CH2Cl2 is a polar molecule with polar bonds. I'll be honest, there's not a lot of compounds that would otherwise fall in the nonpolar with polar compound, with polar bonds. Very few. Tetrachloromethane is one of them. It's also extremely toxic. It will kill you. So you don't work with it very often. Another one that you guys maybe have heard of would be forever chemicals. So this is really hard to draw, to be honest. It probably would have been easier to draw a condensed structure. But this is a polyfluorohydrocarbon structure. So I think that might have been easier to write as CF3, CF24, CF3. Only polar bonds between carbon and fluorine. Well, I guess it does have nonpolar bonds as well, carbon to carbon. But all of those bonds, carbon to fluorine, are very polar. But the molecule as a whole lacks zero symmetry. It's very symmetric. So because of that, all of the individual dipoles cancel each other out, and the molecule at large is not polar. Okay. So what I want us to do next is look at those molecules along the bottom and determine whether they are polar, nonpolar, or ionic. Ionic would be recognized how? What could we look for to determine that something is ionic? Look for a metal, or look for polyatomic ions, things that you recognize as polyatomic ions. But otherwise, if you've got a metal, it's a really good indicator of something ionic. And to be honest, some molecules are really hard to classify as just polar or nonpolar. We've got these very long molecules that are fatty esters, fatty acids, incredibly nonpolar carbon chain, but a very polar CO2H head. So some molecules aren't as easy to classify as just polar or nonpolar. Things like surfactants, your soaps, or your phospholipid bilayer in your cells, they've got incredible properties because of the fact that they are both polar and nonpolar, amphiphilic, if you will, loving both things. So take about 5 minutes, work in groups, go through those compounds you see below, and try to classify them as polar, nonpolar, or ionic. Let me know if you've got questions as you go through it.
Yeah, and also because there's a most 0.5 threshold. It's 0 to 0.5 is non-polar, and then 0.5 to 1.9 is polar, and anything above 1.9 is zero. So this one's ionic, since Na is a metal.
So it tips the scale. Yes. Yeah. You said non-polar on this one?
This is one of those ones, like this is one of the non-polar chain of hydrogen and carbon, but then you've got this at the end, like polar. So it's polar, but
Right.
this part's gonna be a
But when after it, even though chlorine is also electronegatives compared to carbon, it's pulling in equal directions. So it cancels out. So it's still
chlorine, I'd say this is polar. Because the chlorine is gonna pull against. Yeah, I mean, this is kind of the same, but it's on a very long, oxygen is there.
Oh, in the middle, CH. But if it was CCl3, it would be polar.
This one's interesting because you. The oxygen is there.
that means there's also probably a long
Oh, wait, the next one?
Drinking beer at 9
I
a.m.
know, isn't that crazy?
Wow.
A ginger mule, too.
It's even worse than a beer at 10 a.m.
These things are so good.
I heard you guys say something about CCl3, and you said it also has a what?
We were looking at this and
I missed the hydrogen.
Okay, good, because I thought I remembered it's showing an H.
If it was just CCl3,
Well
it would
then,
be symmetrical, right?
would you?
Is 3 bonds not symmetrical?
3 bonds is not an octet, first of all. That's
Over C, right?
that would be a problem. So if it was CCl3 plus, that would be trigonal planar, and it would be fully symmetric. Yeah.
Which would make it polar.
Mm-hmm. Non-polar. But by having that H, it lacks some symmetry. That hydrogen is a different bond type than all of the others, so there's going to be some plane of symmetry you try to draw where it doesn't correlate. It doesn't reflect.
this has never really made sense to me, but I realized polar sounds a lot like polar.
Yeah, I had general chemistry professors that would say, imagine that a dipole is literally pulling on electrons. And if your pulling is equal and opposite, nothing gets pulled. Imagine putting 2 Clydesdales on opposite sides of a cart and then having the Clydesdales pull against that cart. Where's the cart going to move?
Not going.
It's not going anywhere.
So something like this, just by looking at it, knowing that it's symmetrical, you know that it's non-polar.
maybe because it's symmetrical, maybe because there's no polar bonds.
Well, that too.
That, I would say beyond symmetry, the idea that it lacks polar bonds is what I'd go for. You know what I'm saying? I think here you're leaning into the symmetry too much. Yesterday I gave 2 rules. First, must have polar bonds. Second, it must lack some amount of symmetry.
Okay, so it has to meet both criteria.
Got to meet both. And I would say it's got to meet that first one first. If you've got no symmetry but no polar bonds, then it doesn't matter anyways. Sammy, right?
Yes.
Good to have you back.
Thanks.
I was excited to see your compound
Oh, yeah.
involved in your interest in brewing.
Yeah.
That's great. Easy work, Rowan.
Hopefully, if it's correct.
Looks good from here. Oh, except for this one.
This one?
Yeah.
Is that not, that's unsymmetrical?
Well, it depends. What do you think the geometry is at that central carbon? Is it linear geometry, trigonal planar geometry, tetrahedral? Yeah, trigonal planar would be a carbon that has 3 electron regions. And I see 3 electron regions to the chlorines, but that hydrogen would make a 4th electron region. And that hydrogen hints at one of the tips I gave yesterday, which is you got to have polar bonds. Well, carbon to chlorine's polar. You also have to lack symmetry, so you've got to have different bond types or have lone pairs. The idea that you've got a CH and a Cl bond means that you'll never find symmetry between the H and a Cl. So you'll always lack some amount of symmetry because of that. So you're going to lack symmetry. It will have a net dipole. Good work, guys. Mega group is at it again. Everything looked good here.
I think so. I was debating between these ones, whether they were polar or ionic.
Tell me what makes you lean between ionic, lean towards ionic.
Polyatomic ions is what we said.
Where is the polyatomic ion? OH minus is a polyatomic ion. It would need to be in an ionic pair then. So if you're saying that this is OH minus, then you're saying that you've got CH2, CH2, 2+. But we wouldn't show a covalent bond between ionic compounds. Ionic compounds don't have covalent bonds. So the fact that the OH has an explicit covalent bond, it's not ionic, right? Think about it this way. Would you agree that that bond you see is O to carbon? Is that a polar bond or an ionic bond? That's definitely a polar bond. So you recognized OH, and you know that OH minus hydroxide is a polyatomic ion, but this is not hydroxide because it's shown covalently bonded in the molecule. Just polar. Great. Now with the one that has the 6-membered ring and the 3 double bonds, the aromatic ring, I think you could argue that it's a little bit polar, a little bit non-polar. Those of you that did lab yesterday, you guys saw, and those of you doing lab today, you saw that benzoic acid doesn't really dissolve in water, but it does dissolve in a non-polar solvent, or with a, well, it is polar still, but not as polar as water. So just by being polar doesn't mean that it's super polar. Got really quiet when I said that. Okay. Okay, you guys ready to go over them? Do you have any that are specifically challenging? This first compound is called cyclopentadiene. Those of you in lab will use this as a reagent in the last experiment. Polar or non-polar? Non-polar, it's only got non-polar bonds. So it falls into our top category, non-polar. How about this next one, 1-bromobutane? another reagent that you'll actually synthesize during lab this semester? Polar, because it's got this one polar bond. And remember, the difference in electronegativity between C and Br is less than the difference in electronegativity between C and H. But the bond length between C and Br is much, much longer than the bond length between C and H. And both of those bond length and difference in electronegativity impact polarity of the bond. So we have one polar bond and that one carbon that has different bond types. So a polar molecule overall. Isopropyl alcohol, rubbing alcohol. Definitely polar. Chloroform. Now there was a lot of debate, I think, in the room about this one being non-polar. Because of the way that it's drawn, I showed the 3 Cl bonds, and I did not show the hydrogen bond. So it looks like it's a trigonal planar molecule. But that central carbon does have 4 distinct bonding regions. If it's got 4 regions, it's going to take a tetrahedral shape. If it's tetrahedral and one of those groups is hydrogen, then there's some amount of symmetry that's going to be lacking. That hydrogen will not be able to symmetrically reflect into a chlorine. So polar, but I do want to say, somebody brought up, if this was a positively charged carbon, if it didn't have that H, then it would really be just 3 electron regions. It wouldn't be tetrahedral. It'd be trigonal planar. And by being flat, it would be completely symmetric. So this would be nonpolar, despite being an ion. Did you know that ions can be nonpolar? There is a big difference between having a charge and having partial charge. Actually, I'm subbing for another OChem class, and I gave this example when we were doing formal charges yesterday. Do you guys know what formal charges would go on carbon and oxygen? Positive, negative, neutral? Negative where? Carbon's negative. Carbon with 3 bonds and a lone pair is negative. This is carbon monoxide, CO. So it's not a negative ion. There's got to be a counter positive charge to it. Where? Right. Not a lot of places for it to go. Oxygen with 3 bonds is positive. What's the dipole between carbon and oxygen? Which way does it point? Does the dipole point towards oxygen or towards carbon? It points towards oxygen. So if we were to draw a dipole moment, or if we were to draw the partial charges, how fun. A negatively charged carbon is still partial positive. A negatively charged oxygen is still partial negative. Isn't that wonderful? Gavin? These are formal charges, which is more like bookkeeping. It says where are the electrons in the molecule and at what atoms. These are more descriptive about how the charge really represents itself. So despite the fact that both of them have a lone pair, more of the shared electron density is found around the oxygen than it is around the carbon.
So the partial charges, that's based off of the electronegativity, whereas the charges are based off of just the formal charge, which is the electron count.
Yes, electron counts is the formal charge, so it's really just bookkeeping, but this is electronegativity, absolutely. Okay, another molecule that I think is fun, if you look at nitrate, NO3 minus, nitrate has resonance, which means that it doesn't have a negative, it doesn't have a double bond isolated in a specific spot. It's got its double bond spread out across all 3 oxygens. That's a trigonal planar molecule. It is symmetric. It's negatively charged, but it's nonpolar. It doesn't have one region that's more negative and one region that's more positive. The outside of that molecule is all net negative, more negative than positive. So it's nonpolar, but it's definitely an ion. Like the idea about polarity and partial charge are completely separate ideas. How fun. Okay, the next compound we had was this triple bond inside of a carbon chain. Polar or nonpolar? Nonpolar, there's no polar bonds. Then we've got this oxygen-potassium organic compound. That potassium gave it away, right? You saw potassium. You know that this could be represented as K plus O minus ionic. Okay, and then this dibromo compound. Polar. Again, it's got like this one region that's a little less polar and one that's definitely more polar, but overall we'd call it polar. Down below, NaCCH. I've got a triple bond between C and C. Gave it away was the sodium, right? We could represent this as Na plus and C triple bond C minus. All right, vinyl chloride. This is the precursor to PVC pipes, PVC plastics. Vinyl chloride, polar. If you guys remember the train wreck in Ohio that released a bunch of vinyl chloride into the air that burned and then pumped out hydrogen gas or hydrochloric acid as a byproduct? This is what was burning in that train wreck. Glycol, ethylene glycol. Ooh, I'm getting 2 answers, but only 2 answers. What do the rest of you think? Raise your hand for polar. Raise your hand for nonpolar. It's like a 50-50 split. Okay, so let's hear the arguments. Can I hear from somebody for nonpolar?
I said nonpolar because both the OHs are polar bonds, but it's like symmetrical, so they're both pulling like equally.
Cancels out. Okay. Can I hear from somebody for polar? Andrew?
They're canceling out, but wouldn't it have to be linear to be non-polar? So polar molecule?
Right. So this is a good point. If they could align themselves in specific ways, if those CO bonds could align themselves 180 degrees apart, then I think we could say they might cancel each other out. I think more than that, though, it's not just the CO bonds that are polar, but it's also the OH bonds. So we've got to consider how the sum of the OH and CH comes together. So that's going to give us 2 regions, one that gives a dipole like this and one that gives a dipole like that. And I would say these are parallel, opposite to each other, but they're not aligned opposite. They're just in different parts of the molecule. So it's almost like your molecule has 2 major dipole moments. Another thing about these molecules is they are floppy guys. They spin around. They're not rigid sticks. They're more like wet spaghetti. They can spin, and we'll talk a lot about that spinning. So I want you to imagine that we redraw this molecule like this. What I've done is I've gone from a zigzag to a zig-zig. You see that? That is legal terminology that I will use all semester. And now my dipoles point like this. This is just because the molecule has freedom of rotation. And this would actually make me think that the dipoles sum together a lot more. That was a challenging one. Yeah. It's polar, though. That's a polar molecule. And I think we could argue that there are certain orientations of the molecule where the entire molecular dipole is stronger and orientations where it's weaker. But overall, it is a polar molecule, not nonpolar. Yeah, great debate. I loved that. Okay, this next one is methyl cyclohexane. We'll talk more about nomenclature next week. Polar or nonpolar? Nonpolar. This next one is benzoic acid, polar or nonpolar? Yeah, and like I was saying to some of you guys earlier, I think we could argue that this has a non-polar region and a polar region, but not quite as drastic as these longer hydrocarbon chains. This next compound with bromine and oxygen, polar compound. And then the last one, a simple hydrocarbon chain, non-polar. Great. Questions on that? Fun stuff. The reason that we talk about polarity here is so that we can understand how different compounds interact with each other. This is for the 4 of you. Directly behind you, Evelyn. This is for the 2 of you. Oh, thank you. You're welcome. This is for you 2, for the 3 of you, and for the 2 of you. Thank you. Whether a molecule at large has a dipole or not impacts the way that it interacts with other molecules. I told you guys that chemistry is really just the study of magnets. Strong magnets, weak magnets, specialized magnets. And a molecule that has a dipole is a stronger magnet than a molecule that doesn't have a dipole. You may have learned in Gen Chem, like dissolves like. I hate this saying. I think that it's too simple. So we'll say things that are polar dissolve things that are polar, things that are non-polar dissolve things that are non-polar. That dissolving is a matter of intermolecular forces, these molecules coming together, sharing these magnetic interactions. What I like to say instead is strong dissolves strong. For example, I was just refilling our cooking oil thing in our kitchen, and as I'm pouring in the oil from the big container, all this air is getting trapped inside of it, and I leave it to sit, and you can watch the air bubbles climbing their way out of the oil. Oil, polar or non-polar? Non-polar. Air, nitrogen, oxygen mostly, polar or non-polar? Non-polar. N2 and O2 only bonded to themselves, non-polar molecules. So why did I have these bubbles? Shouldn't they have just dissolved in? They're very like. They're non-polar and non-polar. Shouldn't my air have just dissolved into my oil instead of just forming these bubbles that make their way out? No, because oil has very strong interactions with itself, despite being non-polar. Oil has these long hydrocarbon chains, and those long hydrocarbon chains have a lot of surface area to make small, weak interactions a lot of times. So oil is actually interacting with itself quite strongly, and it doesn't dissolve air, which interacts quite weakly. So it's not just like dissolves like, it's strong dissolves strong, and the weak is left to weak. Whatever has weaker interactions with other molecules gets kicked out because those other molecules want to interact more strongly with each other. Oil and water don't mix. But do you know what has stronger interactions within itself? Kind of a weird question. Oil has a higher boiling point, which means I need to put in more energy to get molecules of oil to turn into the gas phase. Oil molecules have strong interactions, so I need to put in a lot of energy to break those interactions. And yet, water doesn't mix with oil because water interacting with itself has a different type of strong interaction. It's got hydrogen bonding to interact between molecules, and those small but strong interactions pull the water together, leaving the large but weaker types of interactions with oil together. I think it's silly to simplify it and say like dissolves like, and it's a much more interesting conversation to talk about how the different types of interactions play a role in what is going to work with what. But the reason we talk about intermolecular forces, especially in organic chemistry, is because we have a goal of running chemical reactions. And to run a chemical reaction, we need to get molecules of reactants to find each other, run into each other with the right orientation and the right energy at the right time to make and break chemical bonds in the way that we want. And the way that we facilitate these molecules getting that energy and finding each other is we mediate the reaction in a solvent. It serves as a medium for the chemical reaction. Sometimes that's gas phase, and so the air is the solvent, but a lot of times that's in a liquid solvent. So we need a solvent that can dissolve all of our different reactants so that we can get them to mix together. So we need to know how they can interact. How can these molecules interact with each other so we find the best solvent for everybody? So intermolecular forces, IMFs. The weakest one is van der Waals forces, also called dispersion, also called London dispersion, also called instantaneous dipoles. Because no one could take credit for this, and no one wanted to just give it a generic name. Instantaneous dipole or dispersion would be the best name that doesn't rely on a dead guy. For the longest time, I thought London was talking about like University College London, but it's actually a guy, London. So I like these names the most, but I do go with van der Waals more often than not because it's prevalent in a lot of different scientific communities to call it van der Waals forces. This is the weakest type of intermolecular force. It's also the most prevalent. Everything, if it is matter, it has van der Waals forces. This is the foundation of intermolecular forces. It increases with surface area. So the larger your molecule, the larger the odds that you have an instantaneous dipole, so the more likely you are to have an instantaneous attraction to a neighboring molecule. But it's fleeting. It actually works on the principle that your electron cloud, which remember makes up most of the size of the molecule, your electron cloud has electrons shifting all over the place. So you create these moments where your electron cloud is further away from your nuclei. Partial negative region and a partial positive region. But because electron clouds are just moving, those regions move around all the time. So you get these instantaneous partial charges across the molecule. The larger the molecule, the more chance that you have those instantaneous dipoles to interact with other molecules. Very small van der Waals force, very large van der Waals force because of surface area. Another interesting application here is structural isomerism in hydrocarbons. This is a molecule called pentane. Pentane is not a very long carbon chain, it's just 5 carbons. Neopentane takes those 5 carbons and it organizes them differently. Instead of having a continuous chain, neopentane has 4 carbons all connected to one central carbon. Which of these do you think has greater surface area? They have the same mass. Same chemical formula, same mass. Both of them are C5H12. Pentane has more surface area. I agree. The way that I like to visualize this, neopentane, tetrahedral center, looks a little bit like a basketball. It's got this spherical shape. And if you try to get these basketballs to touch, imagine coating a basketball in Velcro and then trying to get them to stick together. Where are they going to touch? Just right here. That's it. Now take that basketball and cut it open and lay it flat. You have just increased the surface area because now everything that was on the outside is still on the outside, but everything that was on the inside is also now on the outside. And that's what we get with pentane. It's this longer structure, and you get that van der Waals force all the way along the chain. I actually misunderstood this for a long time, well into tutoring organic chemistry after grad school. I really believed molecular weight had something to do with van der Waals forces, or something to do with intermolecular forces. But molecules, even like things you might think of as big molecules do not experience gravity like we do. Molecules experience electromagnetic force way more than they experience gravity. So molecular mass plays no role here. It's just intermolecular forces. Which of these two compounds, pentane or neopentane, do you think is more likely to become a gas first? If I took two samples of these at a cold temperature, and they're liquids, and I start increasing the temperature of the room, which one of them do you think will boil and turn into a gas first?
C5H12.
They're both C5H12. That's the problem. Pentane will turn into a gas first. Is that what I heard? Neopentane will turn into a gas first. Why? Less surface area, less intermolecular force, less van der Waals force, less holding it together. So it's going to be a lot easier to just flick these off of each other because they're hardly holding on as it is. It's going to be harder to get these to move away from each other because they're holding on more tightly. Good. Good review. What's our next strongest intermolecular force? Hydrogen bonding is not next. Dipole-dipole. Some people call this dip-dip. That is when you have two dipoles interacting. There's different ways that you can have dipoles interact. You can have that end-to-end interaction. The partial negative of one side is interacting with the partial positive of the other. Or you can have them oriented opposite. Oops. So they're kind of interacting in two different places. Right? Head to tail, or head to tail. There's got to be a way to describe that. In line with each other or kind of back to back. Not everything experiences this, right? Only experienced by I'm going to not spell experienced and just say felt. Polar compounds. If you do not have a molecular dipole, you cannot participate in dipole-dipole interactions. Both molecules, whether those are two molecules of the same compound or two different molecules, both molecules must have a dipole-dipole interaction. So, for example, acetone can interact with acetone by dipole-dipole interaction. And a lot of those other compounds, 1-bromobutane can interact with itself by dipole-dipole interaction. Here's a partial negative on bromine interacting with a partial positive on carbon of adjacent molecules. And then all the way over here, we just have that weak van der Waals interaction. The next strongest type of intermolecular force, no, actually, this is hydrogen bonding. Actually, I want to give one more example here. I've given you two examples of like molecules interacting. I want to give you an example of different molecules interacting. If I have acetone in a sample and I have that 1-bromobutane that we were drawing, I can have the partial positive of one interact with the partial negative of another. Bromine is partial negative. It interacts with the partial positive on acetone's carbon. Oxygen is partial negative. It interacts with the partial positive on the bromine attached to the carbon. Different molecules interact with each other because of this feature. If I wanted to get rid of my bromo compound, I might just spray in some acetone because acetone will interact with it, dissolve it, carry it away. Hydrogen bonding is one of the worst named things in in all of chemistry, because it's not a bond by our definition of a covalent or an ionic bond. It is much stronger than these other two forces. It's actually just a specific type of dipole-dipole. It's limited. Hydrogen bonding occurs when a fluorine or an oxygen or a nitrogen is bonded covalently to a hydrogen, and then that hydrogen interacts with the lone pair on a fluorine or a nitrogen or an oxygen. This little diagram can be a little confusing. So what I'm trying to say is it does not matter what combination you have here. No, hydrogen does not make 6 bonds. But a hydrogen bonded to a nitrogen can interact with the lone pair on a fluorine. The hydrogen bonded to oxygen can interact with the lone pair on a nitrogen. I don't know why I flipped my O and N there. Any combination works. These are just incredibly strong partial positive on hydrogen with very strong partial negative on these lone pairs for our other atoms. So you'll recognize that these atoms are very electronegative, fluorine, oxygen, and nitrogen. And it's that electronegativity that is creating that strong dipole, and it's that strong dipole that's allowing for hydrogen bonding.
If I remember correctly, if you see a molecule with both oxygen and hydrogen, it's not necessarily hydrogen bonding.
Good.
Unless the hydrogen and oxygen are bonded together.
Good. So here I have two molecules that have both oxygen and hydrogens, but there's no hydrogen bonded to oxygen. So can these two molecules experience hydrogen bonding between each other? No. I could maybe find a hydrogen that interacts with the lone pair of an O, but there are no hydrogens bonded to these atoms, which means the partial positive on that H is just not strong enough for there to be hydrogen bonding. No hydrogen bonding. What do these two molecules experience instead? Dipole-dipole. If I have ethylene glycol, can ethylene glycol hydrogen bond? Yeah, because the hydrogen of one OH group can interact with the lone pair of another OH group. In fact, ethylene glycol can hydrogen bond a bunch because it's got all of those OH groups. Okay, so those are like molecules. What if I took isopropyl alcohol and I mixed it with acetone? I take rubbing alcohol and I mix it with acetone. Can those two molecules hydrogen bond? Suray's saying yes. Some of you are feeling a little more skeptical.
Yeah. Between the H.
Exactly. This OH qualifies for hydrogen bonding. So yes, isopropyl alcohol hydrogen bonds with itself, but it also has a lone pair on acetone's oxygen that can receive a hydrogen bond. So we say H bond donor, H bond acceptor. H bond donor donates its lone pairs. H bond accept. Actually, I don't know if I don't like calling. I'm not going to ask you to call them donors or acceptors. I have heard that language used, but I feel like it's not a great lineup right now. Anyways, different molecules. One that lacks the capacity for hydrogen bonding within itself, one that has the capacity for hydrogen bonding within itself. They can hydrogen bond between each other. Okay, now the last intermolecular force. Ionic is actually one we'll skip because ion-ion interactions are sometimes called intermolecular, but they're sometimes considered a bond itself, the ionic bond. So I'm going to skip ion-ion interactions. And instead, we should talk about ion dipole, how a dipole interacts with an ion. So in order to consider ion dipole, I almost always have to have two different molecules. An exception there might be if we look at amino acids. Amino acids can have ion-ion interactions, but they also have dipoles, so they could have ion-dipole interactions between neighboring molecules as well. An example that I like, though, is if we take some of these organic ions that we've talked about the last couple of weeks, like NaOCH3, and I want to show how it can have an interaction with a dipole in a molecule. So I'll take NaOCH3 and I'll mix it with CH3OH. CH3OH is methanol. That's a liquid at room temperature. NaOCH3 will be cleaved into Na plus and OCH3 minus. You guys agree? That's the ions that are truly present, and if it can dissolve, it will separate into its ionic pairs. This we would say ion-ion interaction, but we're actually overcoming the ion-ion interaction by having partial charge oxygen interact with sodium and partial charge hydrogen interact with the anion oxygen. The dipole of methanol interacts with the two different ions of sodium methoxide. Obviously, we can say the same thing about water instead of methanol. We could use ethanol. We could use isopropyl alcohol. We'll use alcohols a lot because of that property. One more that I want to show you. Acetone. Acetone's a great solvent for a lot of different stuff. If we take acetone, we can introduce it to salts like potassium iodide. I've got that shown wrong. Potassium iodide will show this ion-dipole interaction between the partial negative O and potassium ion, partial positive carbon, and the iodide ion. We'll use organic salts and some inorganic salts to do some of our chemical reactions. So it's important that we dissolve the salt in a solvent that can have good interactions, strong interactions with the salt. If we took a solvent like hexane and we mixed it with a salt, the only interaction would be van der Waals, and that's a very weak interaction. A nonpolar compound is going to do a terrible job dissolving a salt. Polar compounds, much better job.
Are you saying it broke the ionic bond because the dipole forces were
That's correct. I am saying that dipole ion outweighed the ion-ion.
Is that always true?
Well, it is simplifying it a little bit. Typically, our solvent is present like 1 billion to 1. You've got 1 billion times as many solvent molecules as you have what you're dissolving in the solvent. Maybe 1 billion is a bit exaggerative, but a lot more solvent than solute. So this is a process called solvation. We take an ionic pair and we break the ions apart by solvating the ions. So we don't just get one partial negative to that positive, we get a bunch of partial negatives to interact with that positive. Now I've shown 2, and 2 ion dipoles might outweigh the ion-ion interaction, but I haven't even begun on my 1 billion to 1 interactions. All of these partial negative charges from all of the solvent molecules can wrap around those individual ions, pulling those ions apart from each other, solvating the ions.
Dissolving NaCl and H2O is a really good example of solvation, right?
Great. NaCl, table salt, sprinkle it into your water. Your water solvates the ions,
Just rips the ions apart.
wraps the ions in water molecules, interacting all of the partial negatives of the water with the sodium, all of the partial positives of the water with chloride, breaking the ion-ion interaction, replacing it for a ton of ion dipole interactions. This is how we dissolve salts, solvation. Questions, Saray?
Kind of. So would that be a more stable, I guess, energy state for these ions?
Yeah, actually, dissolving ions is sometimes endothermic and sometimes exothermic, which would say if it's exothermic, solvation is more stable. If it's endothermic, solvation actually requires more energy. It's typically spontaneous, so it will happen without external intervention, although spontaneous does not always mean fast, so it might be slow.
Is there a reversal or opposite to solvation?
Precipitation? Yeah. But typically, if something will dissolve, it's hard to get it to come out. What you might need to do is just boil off that solvent, because the solvent will boil, but the ions will not.
Did you reverse the KSP?
The solubility,
Yeah.
drop the temperature
Yeah.
to make it precipitate, yeah. Or common ion effect, you could add something in there that precipitates with iodide. Potassium, though, doesn't precipitate, so you're stuck. Okay, I want you guys to go through this top part, intermolecular forces. 2 things I want you to consider. What is the strongest force that each molecule could have in a pure sample? So just that molecule with itself. And what are the strongest forces that these 2 molecules can have in a mixture? These are the 2 ways that I typically ask you guys about intermolecular forces. I will ask you what forces, okay, maybe there's 3 ways. In one compound, what's the strongest force? In 2 compounds, what's the strongest shared force? Meaning in pure samples of both, they share this intermolecular force in common. This is their strongest intermolecular force. Or 2 compounds, but strongest between them. The way I usually phrase this is, especially the middle one, if you have pure samples of the two compounds, what is the strongest force shared, the strongest force common? That's what I want to say. What is the strongest force common to the two pure samples? Or I'll say, what is the strongest force in a mixture of these two compounds? I know that can seem a little confusing. What I want you guys to think about, though, as you go through these sets, you can see how they're in sets of two. Think about each molecule individually. What is the strongest that it would feel in a pure sample? And then think about if they were mixed together, what is the strongest force that they'll experience in that mixture?
Could you drop the first one?
Yeah.
Very well.
Thank you. So for the first, oh yeah, I'm sorry. The printer was struggling. You guys are okay with van der Waals if I erase that? You're good? So the first one is a 6-carbon chain and a 4-carbon chain with a 1-carbon group and a double bond. The strongest force in pure samples is van der Waals force for both of them. In a pure sample of either, they're only experiencing van der Waals. And so in a mixture between the two, their strongest interaction is still van der Waals force. Does this seem like a easy way to approach it? Okay, let's take maybe 5 to 7 minutes to go through these, and let me come around and answer questions as you have them.
So, when it's just like a singular molecule like this,
Yeah.
it's a polar bond, but it's only one polar bond, so
Mhm.
it can't be dipole-dipole since there's only one dipole. That makes sense?
Yeah,
I'm making things up.
I think you're making things up, yeah. What about this molecule? Where did I put it? This molecule only has one polar bond, and it definitely has a dipole. So the two molecules have just one molecular dipole. The molecular dipole agrees with the bond dipole. In the event that I have multiple dipoles, the molecular dipole might not look like either one of the two bond dipoles. It might be a hybrid of the bond dipoles. But the molecular dipole still exists. The molecular dipole still exists.
So even if there's just one polar bond, it's still dipole.
Even if there's just one polar bond, if it's a polar molecule, dipole-dipole interactions. Yep.
Because the oxygen doesn't have its hydrogen it needs for the hydrogen bonding.
But it would get it from here, no?
Oh, CH is not a hydrogen bond donor. OH, NH, FH, but CH doesn't have a strong enough dipole to be able to participate in hydrogen bonding. If your hydrogen is not bonded to one of these, it is not a hydrogen bonding component. Otherwise, why don't I have hydrogen bonding here, right? Okay, sure. But if I took this molecule and I mixed it with acetone, like this, lone pair to a CH, those should hydrogen bond then, right? But you would actually find that these make two different layers. They separate from each other.
So I'm thinking that you have CH and the H's are coming off of the hydrogen.
Yep. You do have CH, and the H's are coming off of the carbon. But those hydrogens don't participate in hydrogen bonding. They don't have a strong enough partial positive. This partial positive is formed because of the bond to the very electronegative atom. Carbon is not electronegative enough to put the partial positive needed for the hydrogen bonding. So a CH never will participate in hydrogen bonding. Good. Yes?
I'm confused on how ion dipole bonding works.
Sure. Well, interactions. Let's not call it bonding. If I could rename hydrogen bonding, I would.
Okay.
I'd stop calling it bonding as well. You see the O's are all surrounding that potassium,
Yes, yeah.
and that's because the potassium is positively charged and it attracts the partial negative of the acetone's dipole.
Okay, so is it always an oxygen bonded with a positive?
Not bonded.
Or
Interacting with. Yep.
A positive.
No, it's always a negative. It's always a partial negative atom.
Okay, it doesn't have to be an oxygen?
Doesn't have to be oxygen.
Okay.
Yep. It could be a halogen. It could be a nitrogen.
But as long as there's that like partial negative, partial positive, that's what makes it ion dipole.
Exactly.
Yeah.
The dipole comes from the acetone molecule, the ones that are surrounding Ki. That's the dipole part of the interaction. It is not it's not positively or negatively charged,
Okay.
but it has more negative regions
Yeah.
and more positive regions. So the more negative region interacts with K+, the more positive region interacts with I-. The dipole interacts with the ions. They were bringing up water before, and we could show that like this. That partial negative on the oxygen of water surrounds the sodium plus, solvates it, traps it, almost like in a little bubble. Meanwhile, on the outside is a bunch of chlorides, or is a chloride, surrounded by the partial positives of the water. The dipole of water interacts with ions in different ways. Different ions interact at different parts of the dipole. Maybe this one was confusing because I showed it almost as like a complex, like they're bonding right next to the ions themselves, but they can very much form these like spheres of interaction.
That can have an interaction with the lone pairs of the oxygen.
So, okay, there's lone pairs on this oxygen.
Yes, because oxygen has 6 valence electrons, but there's only 2 bonds.
Okay. So
Honestly, if it's Act 2,
this side of the
Throw back to your childhood.
I was like,
Rewinding your hair style.
you are a great teacher.
Making sense of it?
Yeah.
NH2 and the H2N and it's there's
Trying. Any questions?
No way.
Good as gold?
well, you know, anytime you know hydrogen is bonded to the iron.
So, the one on the left
That's all
alone
that's the iron.
are together technically bond would be the second molecule. Because that second molecule has that.
So does that oxygen.
The one on the part is the between molecules. The ones on the under are the
But these two.
Oh, we did that one.
So why are these hydrogens allowed to bond to oxygen, but the ones in carbon are? Because of the electronic.
As well as these carbons won't have a low valence group.
Yes. Right.
For
And the hydrogens do. Wait.
No, but but in this compound, there are,
That was a weird silence that fell over the room. So Delaney, your question's valid. Why can't every hydrogen be a part of hydrogen bonding if there's a lone pair to be donated to it? And the idea is the partial positive on the H is not strong enough to make it that strong of an interaction unless the hydrogen's bonded to.
A nitrogen, oxygen, or fluorine.
Yep.
Okay.
Okay, so for lab this week, you're taking advantage of intermolecular forces to dissolve a mixture. You're taking diethyl ether and you're dissolving naphthalene and benzoic acid. What is the strongest intermolecular force that benzoic acid has in a pure sample? It can hydrogen bond because it's got an OH, so it's got lone pairs and H's to engage in hydrogen bonding. What about naphthalene? Strongest in a pure sample? Just van der Waals forces. What about diethyl ether? Yeah, dipole-dipole. But when I mix them, what is the strongest force experienced between these in a mixture? Still van der Waals. Because naphthalene has no partial charge, no heteroatoms, no dipoles. So these are only experiencing van der Waals force. And what about these? Hydrogen bonding. Because diethyl ether has lone pairs that can hydrogen bond with benzoic acid. Isn't that interesting? In and of itself, diethyl ether is kind of right in the middle in terms of intermolecular force strength. But it's able to dissolve both of these compounds using different types of intermolecular reactions, intermolecular forces. Okay, what about here? Strongest intermolecular force in xylene on the left, van der Waals, and in this ketone on the right, dipole-dipole, and shared between them, just van der Waals. You're only as, well, I would say you're only as strong as your weakest link, but diethyl ether was only dipole-dipole, but was still able to do hydrogen bonding. So it's not always just the weakest link. How about here, isopropyl chloride, dipole-dipole, and cyclohexanol, and common between them, dipole-dipole. Nice. On the bottom right, I've got this acetylamide and diethyl ether. What about acetylamide? Hydrogen bonding with itself, diethyl ether, and common between the two, hydrogen bonding. I've got this aldehyde on the left. I'm sorry I'm throwing words at you guys that we're going to talk about next week. So don't worry if some of these words make no sense. Aldehyde on the left, dipole-dipole, yes. On the right, the carboxylic acid, and common between them. Nice. You guys are getting it, yeah? Last one, what's common with this diamino group? Can hydrogen bond, and with acetone, dipole-dipole, but common between them. Awesome. Great job, guys. Now into the meat and potatoes of it all. Actually, that's it for intermolecular forces and partial charges. The next 2 days of our lecture, we'll be wrapping up this worksheet, talking about resonance in part and acid-base chemistry, where resonance plays a pretty important role. So I want to transition by having you guys talk to me about what you know about resonance. What does that word mean in your head? And do you have a definition of it? And when I say what does it mean in your head, I don't mean just in a chemistry context, but the word resonance, what does it mean? Vibration, okay. Can you tell me why, Patrick?
Like with music and with sound, like resonance, it vibrates weird, like resonance, and then the instruments as well.
Yeah. I was listening to music once, and the music was loud enough that it made my guitar strings vibrate. It hit that resonance frequency between the guitar strings, yeah. Or I think of opera singers, hit the resonating frequency of glass, which means that those glass molecules are already vibrating, and the sound waves that are now hitting it are in that same frequency, and so it just makes the vibrations big enough that they shatter.
Like in a bathroom stall as well, if you like hum like certain notes though, then like it resonates as well.
Interesting. Very cool. Okay, so this is what I think of as resonance. Same, but different, right? The molecules in glass are vibrating with the same frequency as the opera singer's voice. So it's the same thing, but there are different things and they're interacting. Or if I tell somebody that story really resonates with me, right? I didn't live that story, but I've lived a similar story. Same, but different. This is quite literally the meme that I use to make sense of resonance. In chemistry, how do we define resonance? We say that resonance is the movement or the delocalization of pi electrons. Sometimes those pi electrons are obviously pi electrons. Sometimes those pi electrons look like non-bonding lone pairs, but because they engage in resonance, well, we know that they're pi electrons because they move. The reason that I say movement or delocalization, it depends on what perspective you're taking. A Lewis structure approach, a valence bond approach, shows resonance as electrons moving between different parts of a molecule. No sigma bonds are made or broken, but just pi electrons appear in different places. It's like the electrons move. Molecular orbital theory tells us that the electrons are not moving. The electrons just exist across multiple atoms at the same time. The electrons are in orbitals that span the molecule. So the electrons are delocalized. They're not found in one atom. They're not found between two atoms in a bond. They're found over a series of atoms delocalized over the structure. So we're going to lean into both versions of these because, like we said earlier last week, MO theory does not do a good job of helping us understand structure. But valence bond theory, Lewis structures, doesn't really help us understand why molecules behave the way they do. So I want to start with a simple idea of resonance in a pi bond. The two-atom pi system. So that first molecule that you see, we've been talking about it a lot, that's acetone. There is a pi bond between them. So I should be able to show some resonance. The way that we show resonance is by drawing two structures related by this double-headed arrow. This is not an equilibrium arrow. Equilibrium says a chemical reaction is occurring one way or the other. This is not a chemical reaction, it's resonance. Resonance forms, which are what we're going to be drawing, resonance forms don't exist. A resonance hybrid tells us more likely how electrons exist relative to those different resonance forms. So this is saying not a new structure being created, but a new way of looking at the same structure. So those pi electrons can move. They can either move to the oxygen or they can move to the carbon. But they're not being pulled evenly by both the oxygen and the carbon. Which atom pulls on those pi electrons more? Oxygen, the more electronegative atom. So if we're going to show these electrons moving, we should show them moving to the oxygen. I'm going to draw in lone pairs. We can assume them, but I want you guys to recognize how that change is occurring. These are two resonance forms, but they're not necessarily equal resonance forms. They don't necessarily describe the molecule equally. So a few things that we're going to do. We're going to look at all these resonance forms. We're also going to look at electron arrows. So electron arrows or curved arrows are drawn on one structure to show how electron density changes in the following structure. Electron arrows have to start at an electron source. That means they start at a lone pair, or they start at a bond, and sometimes we'll get away with starting at a negative charge, because a negative charge indicates an excess of electrons. But electron arrows never start at atoms, because the chemical symbols that we're using, those are to describe nuclei. The electrons are always shown as lines or dots. So I want to say on this structure on the left, the pi electrons stopped being shared and were taken exclusively by oxygen. I want to say that the electrons are moving from here to here. So my arrow starts on the pi bond. Which of those two lines is the pi bond? Yeah, what a silly question. I start on either side that I want, but they start at the bond and they point to the oxygen. It's saying these electrons, I want them to move here. And this is what it looks like. We draw arrows on one structure to explain the formation of the next structure. Show how the next structure forms. Okay, so that's one two-atom system. I think I didn't put another two-atom system on here, but well, actually, yeah, the structure at the very bottom of this. I know that these structures might not have come across very well. This molecule also has a two-atom system, but instead of having a pi bond that we can show breaking in one direction or the other, it has pi bonds that can form. Notice here how we had this vacancy on carbon. A positive charge means that there's space for electrons to go into. And we had lone pairs on oxygen, and we know that that could just recombine into a pi bond. So up here, we've got lone pairs on oxygen, and we've got lone pairs, a lone pair on the nitrogen. I think I've forgotten my hydrogen, haven't I? And we can show this two-atom system. So first, let me show how the nitrogen shares electrons, shares a lone pair, and makes a double bond. Lone pair moved from nitrogen to the adjacent carbon. It's that two-atom system. Filled carbon's octet. I'm missing something on the nitrogen. The positive charge. These resonance forms should have the same net charge. Net neutral, net neutral. Resonance forms are not different molecules, so they cannot have different charges. But the way that charge shows up might be different. Net positive, and because oxygen has, because nitrogen has shared its electrons, nitrogen has lost electrons, becomes positive. Now, the three-atom system is a much more common example of resonance. And I'm going to actually show how there's another resonance form with this molecule. But it involves a 3-atom system. Typically, a 3-atom pi system has 1 pi bond and a lone pair or a charge, sometimes both. Well, here is a pi bond between nitrogen and carbon, the one I just formed. And above that is a lone pair on the oxygen. So here is my 3-atom system. Oxygen with its lone pair, and the pi bond between carbon and nitrogen. I think you guys might agree that there's another pi system if we go in the other direction, a pi bond between 2 carbons and a lone pair on oxygen. There's a lot more resonance in this molecule than the ones I'm going to show you. But this is an example of that 3-atom system. What we can see in the 3-atom system is we can push electron density towards a positive charge or push electron density away from a negative charge. So what we'll show is oxygen donating its lone pair to form a double bond with carbon. Bad news, that carbon already has an octet. I can't give it more electrons because it will break its octet. So what I need to do instead is break a bond that the carbon already has. And because I'm showing resonance, I can't break a sigma bond, but I can break a pi bond. I can move pi electrons. So the carbon-nitrogen double bond goes back to the nitrogen. Remember, these electron arrows are starting at an electron source and moving to a bonding region, or moving from an electron source and moving to a non-bonding electron region. The change that we should see in this next resonance form, oxygen and carbon should now have a double bond. Oxygen goes down to just 1 lone pair. Nitrogen gets its lone pair back. And what am I missing? Positive charge on oxygen. Oxygen there with 3 bonds and 1 lone pair takes a positive charge. There is no reason that I couldn't have drawn this last resonance form from the first resonance form. There was a 2-atom system between oxygen and carbon, just like nitrogen and carbon. I could have taken this form and I could have shown the formation of this form directly.
Where did the double bond between the 2 carbons go?
Thanks for pointing that out. It didn't go anywhere. Thank you. I would have missed that. You guys caught that? Okay. 3 resonance forms for that molecule. Which of them exist? None of them. They don't exist. Resonance forms is our way of trying to understand the universe. We are kindergartners, and I'm on the same side as you guys. Our brains are just kindergartners in the world of chemistry. It is so challenging to grasp what these molecules are actually doing, so we simplify it as much as we can. These don't exist. They are all different perspectives on a molecule, but none of them are perfect. So 2-atom systems, 3-atom systems. In reality, though, we look for the resonance hybrid to tell us more like what the molecule looks like. And in this case, the resonance hybrid has this positive charge that is delocalized across the nitrogen, the carbon, and the oxygen. How fun. Notice that I've got a double bond here that is spread out over 2 bond lengths. So it becomes a bond and a half between carbon and nitrogen and a bond and a half between carbon and oxygen. It's not a double bond in either place. If you analyze this molecule, you get into a lab where you have the instrumentation to analyze bond lengths, you don't find a carbon-nitrogen single bond, you don't find a carbon-nitrogen double bond, you find a carbon-nitrogen bond and a half. That is the true nature of the molecule. But that's really hard to demonstrate. Where's the positive charge? It's on all of the atoms. It's not in one place. Where's the double bond? There is no double bond. It's a bond and a half in both places. How fun is that? Same, but different. This is resonance. The electrons are in different places. No sigma bonds have changed. If you find yourself breaking a single bond anywhere, you're not doing resonance. If you find yourself exceeding the octet rule, you're not doing resonance. We said that resonance is the movement of pi electrons. These don't look like pi electrons, but they must be pi electrons because they're engaged in a pi system in one of the resonance forms. If I wanted to draw lone pairs here, it'd be really challenging because the lone pairs make up part of these double bonds. And I can't really show how the lone pairs are present and engaged in the double bond at the same time. Lone pairs just shouldn't be added into these resonance hybrids. Fun? Okay, I want to continue on with this 3-atom system and set us up for an explanation of MO theory that we'll carry on with in tomorrow's class. In this 3-atom system, let's consider a simple molecule. A pi-bonded system of 2 carbons and a carbocation adjacent to that. Because this is molecular orbital theory, we have these 3 lanes, the groups that are coming together and the groups that are together. We're going to look at just the pi orbitals. Remember last week we looked at MO theory and we said how sigma bonding comes together from hybridized orbitals and pi bonding comes together from p orbitals. We're going to look at that again, but we're going to focus just on the p orbitals. The carbon-carbon double bond from last week had 1 p orbital. I'm sorry, I should say has the pi orbital where the pi electrons are in a bonding orbital. And it had pi star, where the orbitals look out of phase from each other, the pi anti-bonding orbital. Now I'm interested in this carbon cation's p orbital. And because it's a cation, I'm going to say it brings no electrons with it. And what we're going to look for is the hybridization of all of these. Last time we had constructive interaction and destructive interaction. But this time we're going to have constructive, destructive, and something in the middle. Last time we took 2 orbitals down and up. This time we're actually taking 3 orbitals. So I should get 3 orbitals back. Here's how they combine. That pi bonding orbital combines constructively with a p orbital. The 3 orbitals all come together for this essentially net neutral orbital. And then pi star comes together with the p orbital. 3 orbitals in, 1 p orbital on each carbon. 3 orbitals out, 3 molecular orbitals spread across this 3-atom system. Oh, it's so good. Last time we said constructive interference on the bottom and then destructive up above. What we didn't say was that as we go up, we're adding a node. Every time we go up an orbital level, we add one node. You guys remember what a node was? Where the what? The nucleus? Where the nucleus would be found right at the node. Someone else was saying something? A node is where the orbital changes sign, changes phase. Think of a wave in the ocean going up and then starting to come down. Right where it meets baseline would be a node. Technically no wave there. And then it goes down, it changes sign, changes phase. Same thing here. We're going to increase a node. 0 nodes, 1 node. 0, 1, 2 nodes. On the bottom, all 3 of my p orbitals are in phase with each other. No nodes between them. One big pi molecular orbital. 2 electrons that are dispersed across 3 atoms. You ever heard of that? A 2 electron, 3 atom center. I say that wrong all the time. 2 electrons, 3 atoms. As I go up, I add a node, and that node will be symmetric in the molecule, which means that it's going to fall right down the middle. And then as I go to the top, a second node, also finding symmetry. So I split my orbital into thirds. I want to draw your attention to where the nuclei are. Also, I'm sorry, I just realized up here at the top I didn't draw my remaining carbon or the positive charge. Where are the nuclei? Here's, oh, you can't really see that, can you? Where's my blue? This is a 2-atom system on the left. So here's one nucleus, here's another. One nucleus, here's another. Here's just a 1-atom system. These are a 3-atom system. 1, 2, 3. 1, 2, 3. Do you see how that node falls over the orbital, or sorry, over the nucleus? That nucleus doesn't have electrons around it. The molecular orbital is on nucleus 1 and nucleus 3, but not on nucleus 2. And then 1, 2, 3. What we're going to show is how the resonance forms look like possible structures, but the molecular orbital tells us things that the resonance form couldn't. 2 electrons, 0 electrons. I'm going to put my 2 lowest energy electrons. I'm going to put my 2 electrons into the lowest energy. I'm sorry, I know I'm running out of time, and we're gonna pick up with understanding the arrow pushing for this tomorrow as well. But these are the 2 resonance forms for this 3-atom system. You can see how it looks like a double bond to the left and a double bond to the right. MO theory says it's not a double bond between these 2 or a double bond between these 2. MO theory says it's a pi bond across all 3 carbons. So it doesn't look like this or that. It looks like this. You'd never guess that from Lewis structures. If you think about this positive charge, it's not on one or the other. It is both at the same time. It's a vacancy on those end carbons. Okay, I'm so excited. We'll pick up here. There is a new active homework. Sorry. So section 2 is also due before the end of the unit test, but remember, no late work penalties. So just get to it when you can. But that active homework is useful for this unit test.
Not section 3, right? Just 2.
Section 1 and section 2. Those are what you should finish on active before your unit test. Okay, I'll see you guys tomorrow.